Chapter 5, Eigenvalues and Eigenvectors, Section 5.1, Eigenvalues and Eigenvectors. If A is an n by n matrix, then a non-zero vector x in Rn is called an eigenvector of A, or of the matrix operator Ta, if Ax is a scalar multiple of x. That is, Ax has to be equal to lambda x for some scalar lambda. The scalar lambda is called an eigenvalue of A, or of Ta, and x is said to be an eigenvector corresponding to lambda. So if, when we take a vector x and multiply it by a matrix, that's the same thing as multiplying x by some scalar, then the scalar is an eigenvalue of the matrix A. And then that vector is called the eigenvector that corresponds to that eigenvalue, lambda. As an example, how about we determine whether the vector x equals 1/2 is an eigenvector of A? Well, if x is an eigenvector of A, then that means that if we take A times x, that should be the same thing as scalar multiplying x. So let's see, we have A is 3, 0, 8 minus 1, and we have x is 1, 2. When we multiply them, we get 3, 6. So that's the same thing as, well, x was 1, 2, so that's just 3 times x. It really did just scale it by 3 by multiplying by this matrix. Notice that wasn't super obvious just by looking at the matrix that would happen to multiply x by 3, but we tested it out and it actually worked. So we say that x is an eigenvector of A with eigenvalue lambda equals 3. If A is an n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation determinant of lambda I minus A equals 0. To see why this is true, just write out the definition of an eigenvalue, eigenvector. That means that A times x has to be lambda times x, but that's the same thing as writing lambda times the identity times x. Right, the identity won't change anything. But then I could just subtract ax, right, from both sides, move it over here, and I would, on this side, I would have lambda I minus a times x, right? I just factor out the vector x. And on this side over here, I would have 0, the 0 vector. Notice I just really switched the sides a little bit. And then having this thing times x equal to the 0 vector means that this determinant would have to be 0. Anyway, we call this the characteristic equation of A. Notice we can't have x to be 0, because then that would violate the definition of what we said an eigenvector was. So let's do another example. In example 1, we observe that lambda equals 3 is an eigenvalue of the matrix A equals 3, 0, 8, minus 1, but we did not explain how we found it. How about we use the characteristic equation to find all eigenvalues of this matrix? So what we'll do is we'll write out determinant lambda I minus A equals 0, and we'll actually write out what the determinant is. Well, lambda times the identity minus A. So the identity is 1, 0, 0, 1. I'll take lambda times that. So I'll get lambda, lambda, and then zeros. But how about I subtract off A now? 0 minus 8 will give me minus 8 over here. 0 minus 0, well, this will stay 0. And then I'll just subtract off 3 and minus 1 from the lambdas. Right? So that's the determinant of lambda I minus a. Basically just replace the ones with lambdas, because lambda is multiplying by the identity. We have ones along the diagonal. We have zeros over here, and then just subtract off all the entries of a from everything left. Anywho, that equals 0, right? So that's the same thing as saying lambda minus 3 times lambda minus 1 minus 8 times 0 is 0. So that's the same thing as saying lambda minus 3 times lambda plus 1. Oops, this is minus 1. This should be plus 1. So that has to be 0. And that means that lambda is either, let me fix that a little bit. Lambda is either 3, but lambda could also be minus 1. So we found 3 before, but it turns out that minus 1 is another eigenvalue of this matrix. When the determinant lambda I minus a is expanded, the characteristic equation takes the form lambda n plus c1 to the lambda to the n minus 1 plus so on all the way to the constant with lambda to the 0 power, which is a constant, equaling 0. Where the left side of this equation is a polynomial of degree n, in which the coefficient of lambda n is 1. The polynomial p of lambda, in which we have lambda plugged in, is called the characteristic polynomial of a. So that's this left-hand side is the characteristic polynomial. It should make sense. Look at the previous example we just did. When we took this times this, we got this characteristic polynomial right over here. If we were to FOIL this out, we'd get lambda squared minus 3 lambda plus lambda minus 3. Simplify, and that's exactly what we would get. As an example of using this, how about we find the eigenvalues of this matrix A? So we'll write out determinant of lambda I minus A. Okay, so that's going to be the determinant of lambda minus 0 is still just lambda. I'll have minus 1 because it's not on the diagonal. So it's just minus the 1. It would be 0 minus 1. And then 0. And then also not in the diagonal, so 0 minus 0 is just 0. Then I've got lambda, all in the diagonal. I'm going to have my lambdas. Minus 0, again, just stays lambda. Then minus 1. Then minus 4. Minus 17 is positive 17. And then I have lambda again. But this time there's an 8, so I'll do lambda minus 8. Okay, so now I need to actually take this determinant. So how about I expand along the first row? I'll just do the cofactors. So I'll take lambda times this determinant. So that's lambda times lambda minus 8, which is lambda squared minus 8 lambda, and then minus 17 is plus 17. And then minus 1 is plus 1 times this determinant, well, this determinant. So that's 0 is going to kill off that guy. Then minus 4 times minus 1 is 4. So subtracting that gives me a minus 4. And then this last 0 kills off all the other terms. So I'll end up with lambda cubed after distributing, minus 8 lambda squared plus 17 lambda minus 4. Okay, so how about we set that equal to 0 and see if we could solve it. Unfortunately, solving polynomial equations is not the most fun thing, but we're up to the task, of course. So I'll rewrite it, but I'll set it equal to 0 so that I can see what lambdas will actually make this determinant 0. I'll use the rational root theorem, which says that possible solutions to this polynomial equation are when we take the last term, divide it by the coefficient of the first term, which is 1. So I'll end up with all of the different factors of 4 divided by 1, which is just 4. So that's plus or minus 1, plus or minus 2, and plus or minus 4. Those are all the factors of 4 divided by 1. And how about I test 4? So I'll take lambda minus 4, and I'll see if I can divide this polynomial by lambda minus 4 evenly. And then that'll mean that 4 is a root, and that lambda equals 4. So I'll stick it inside of lambda cubed minus 8 lambda squared plus 17 lambda minus 4. And we'll see what we get. Okay, so lambda fits in lambda cubed, lambda squared times, multiplying that, I get lambda cubed minus, remember I'm taking lambda squared times lambda minus 4, divide, multiply, subtract, bring down, so minus 4 lambda squared, and I'll subtract that, and I will get minus 4 lambda squared, lambda cubed cancels, I bring down the 17 lambda, and I'll end up with, let's see, lambda minus 4 fits into this thing, minus 4 lambda, right? Lambda fits in the minus 4 lambda squared minus 4 lambda times, I'll multiply, I'll get minus 4 lambda squared plus 16 lambda. Now I'll subtract, and I'll end up with lambda, and then I'll bring down the minus 4. And then lambda fits in lambda minus 4 exactly one time, and there's no remainder. So this means that I could factor my polynomial as lambda minus 4 times, well, my result was lambda squared minus 4 lambda plus 1 after doing my long division, and that'll be equal to 0. Okay, so I identified that lambda equals 4 is an eigenvalue. Let's see if I can get the other ones. Well, that requires me figuring out which lambdas over here make this thing equal to 0. So I'll just use the quadratic formula. I'll set lambda equal to negative b plus or minus square root b squared minus 4ac over 2a, so negative 4 plus or minus square root of negative 4 squared minus 4 times 1 times 1, and all of that's over 2 times 1, so that equals 4 plus or minus square root of 12 over 2, which is 2 plus or minus root 3. Okay, so those are my other two solutions. I've got altogether lambda equals 4 is an eigenvalue, lambda equals 2 plus root 3 is another eigenvalue, and lambda equals 2 minus root 3 is the last eigenvalue. Ready for another one? How about we find the eigenvalues of this upper triangular matrix? Well, again, we'll write out the determinant of lambda I minus a. We'll set that equal to the determinant of, well, I'll just take lambda minus each of these guys on the diagonal. So that's lambda minus a11, lambda minus a22, lambda minus a33, lambda minus A44. And then all of these guys are still 0 minus 0, so it's 0, 0, 0, 0, 0, 0, and then above just the minus versions. Okay, so minus A12, and then minus A13, minus A23, minus A14, minus A24, and minus A34. Okay, so I'll get the determinant of this. Notice, though, that I could just multiply each of the diagonals because it's upper triangular matrix. We saw that the determinant of these guys is just the product of the diagonal entries. You could also see that by cofactoring, you'll end up with this times this determinant, but then you can cofactor again, take this times, well, this times this determinant, and then cofactor again, you get this times this determinant. So yeah, it's just going to be, and I'll put it a little bit lower, it's going to be lambda minus A11 times lambda minus A22 times lambda minus A33 lambda minus A44. So it looked kind of scary because it was a 4x4, but the fact that it was upper triangular kind of saved us in calculating the determinant. Anyway, we're looking for where lambda minus A11 times lambda minus A22 times lambda minus A33 times lambda minus A44 equals 0. And lucky us, our characteristic polynomial already has linear terms all factored out, so we can just read off what lambda equals. It's got to be A11, A22, that should be a comma, A33, and A44. So those are the 4 eigenvalues. So notice we could have just read those off of the upper triangular matrix to begin with, and now we basically have figured out the eigenvalues of any upper triangular matrix by the same reasoning. Which brings us to this theorem. If A is an n by n triangular matrix, upper triangular, lower triangular, or diagonal, you can verify the other cases, then the eigenvalues of A are the entries on the main diagonal of A. How about we find the eigenvalues of this lower triangular matrix over here? See, the zeros make it lower triangular. Again, we can just read them off. So we have lambda equals half, lambda equals 2/3, and lambda equals -1/4. Awesome. If A is an n by n matrix, the following statements are equivalent. Lambda is an eigenvalue of A. If and only if lambda is a solution of the characteristic equation. If and only if the system of equations lambda I minus ax equals 0 has non-trivial solutions. If and only if there is a non-zero vector x such that ax equals lambda x. All of these things we've already seen. By definition, the eigenvectors of A corresponding to an eigenvalue lambda are the non-zero vectors that satisfy lambda I minus ax equals 0. Thus, we can find the eigenvectors of A corresponding to lambda by finding the non-zero vectors in the solution space of this linear system. The solution space, which is called the eigenspace of A corresponding to lambda, can also be viewed as the null space of the matrix lambda I minus A, the kernel of the matrix operator T lambda I minus A from Rn to Rn, and the set of vectors for which Ax equals lambda x. Let's do an example where we find bases for the eigenspaces of matrix A. So what we'll do is we will first write the characteristic equation. So we'll write the determinant of lambda I minus A. In this case, we have lambda minus 1 is lambda plus 1. Then we have a minus 3. And then we have a minus 2. Right? 2, 3. And then we have lambda. Minus 0 is just lambda. Okay, so we'll take that determinant. So that's lambda times lambda plus 1 minus 6 because minus these guys multiplied. And we'll distribute lambda and then factor, and we will get lambda minus 2 times lambda plus 3. We want to set that equal to 0, which gives us eigenvalues of lambda equals 2 and lambda equals minus 3. Much easier when you have a 2 by 2 matrix. So remember, this is the equation. Lambda I minus a times x equals the 0 vector is what we are looking for. This is what will give us the eigenvector that we need. So that's the same thing as we already wrote, lambda plus 1. We have minus 3, minus 2, and lambda, but we're not taking the determinant this time. We're trying to solve this equation, where we're going to write x as x1, x2, an arbitrary vector, and look for solutions that make it equal to the 0 vector. Okay, so let's use our eigenvalues that we got. So we'll plug in lambda equals 2. Well, then 2 plus 1 gives us 3, and we still have the minus 3, we still have the minus 2, and then lambda is 2. So here's what our equation lambda I minus ax ends up becoming. It's just 3 minus 2, 2 times x1, x2 equals the 0 vector. And this is what we're going to solve. So how about we write the matrix together as 3 minus 3 with a 0 adjoined, minus 2, 2, 0, our augmented matrix. And we'll put that in reduced row echelon form by just taking, well, as you can see, the bottom row is a multiple of this row. You could just divide the top row by 3, so you get 1 minus 1, 0, and then add that to, or add 2 of those to the bottom, and it'll zero it out. Okay, wonderful. So that gives us, by reading off the top row, we have x1 minus x2 equals 0, which is the same thing as saying that, how about x2 is some parameter? It's a free variable. So we can make x2 equal to t, which means that x1 is equal to x2, so x1 is also t. Okay, so that means that we have x1, x2 equal to tt. We could factor out the t and get it's t times 1, 1. So any linear combination, because any value of t will work over here, any linear combination of 1, 1 will span our eigenspace corresponding to lambda equals 2. So 1, 1 is a basis for the eigenspace corresponding to lambda equals 2. Okay, what about the other lambda we got? It was negative 3. Okay, so let's do the same thing again. Well, how about I'll do it over here. Lambda equal to minus 3 gives us a different equation to solve. So lambda plus 1 is negative 3 plus 1 is negative 2. I'm going off of over here. And then I still have the negative 3 and negative 2, and then lambda is minus 3. Okay, so now I want this matrix to be multiplied by x1, x2, and we'll see what x1 and x2 have to be to get 0. Okay, so I will again augment my matrix. I'll get minus 2, minus 3, 0, minus 2, minus 3, 0, and now it's super obvious that the row is duplicated. So the top row I'll divide by minus 2, and I will get 1 and 3 over 2 and 0, and the bottom row I'll subtract off and just get 0. Okay, great. So this gives me a top row of x1 plus 3 over 2 x2 equal to 0. So that tells me that x2 again is the free variable. I'll make it t. So moving it to the other side, I'll get that x1 is minus 3 over 2x2, so x1 is minus 3 over 2t, and x2 is just t. So in the first case, we had x1 and x2 are both t, but in this case, x1 is a little bit different. So this means that I have x1, x2 equal to minus 3 over 2t, t, and I'll again factor out the t, and I'll have left minus 3 over 2, write that a little bit better maybe, minus 3 over 2, and 1. Okay, so that means that, or this implies that minus 3 over 2, 1 is a basis for the eigenspace corresponding to lambda equals minus 3. Excellent. How about we do another one? Okay, this time we have a 3 by 3, so the determinant is a little bit more painful to compute. Remember, we're doing lambda I minus a, so we'll get the determinant of lambda, then minus 0, 0, minus 2 is 2, and we'll get minus 1, lambda minus 2, minus 1, minus 1, 0, lambda minus 3. Okay, we'll set that equal to lambda minus 2 times lambda minus 3 plus 2 times lambda minus 2, because lambda times this determinant gives me this, and then the 0 kills off this determinant, and then 2 times this determinant gives me this. Okay, I will distribute out lambda, collapse terms, so that I have lambda cubed minus 5 lambda squared plus 6 lambda minus 4. And I could, oh wait, I'm missing a minus, no, I'm missing a plus 2 lambda. There we go, minus 4. Okay, so then I will combine 6 lambda and 2 lambda, and I'll get lambda cubed minus 5 lambda squared plus 8 lambda minus 4. Okay, so let's set that equal to 0. Lambda cubed minus 5 lambda squared plus 8 lambda minus 4 equals 0. Looking at that 4 divided by the coefficient here is 1, so that's just going to be possible solutions are factors of 4. And we saw this before. Just plus or minus 1, plus or minus 2, and plus or minus 4. Those are all the factors of 4. last time I tested 4 because I kind of knew it was going to work. It takes a long time to test every single one. This time I'm going to test 1. So if I'm testing positive 1 as a solution, that means that lambda minus 1 should be the factor. So that's what I'll divide by. So I'm going to fit that into lambda cubed minus 5 lambda squared plus 8 lambda minus 4. Okay, so I will put lambda into lambda cubed. It goes in lambda squared times. And I end up multiplying to get lambda squared times lambda minus 1 is lambda cubed minus lambda squared. Subtracting that gives me, let's see, minus 4 lambda squared. And then I'll bring down the 8 lambda. And then I'll fit lambda minus 1 into this, and it fits in minus 4 lambda. So multiplying that gives me minus 4 lambda squared plus 4 lambda. And then I'll subtract off. And I'll get 4 lambda. And I'll bring this down and get minus 4. So that fits in exactly 4 times. Perfect. Okay, so that means that I factor out lambda minus 1, and what I have left is this, which is lambda squared minus 4 lambda plus 4, and I'm setting that equal to 0. So that's the same thing as lambda minus 1 times lambda minus 2 squared. I don't have to do the quadratic formula this time because this thing actually factors, which is nice. And that means that I have eigenvalues of lambda equals 1 and lambda equals 2. Sometimes it could take a long time to get through all the possible solutions when you're doing the rational root theorem. Anyway, let's now look at, now that I have my eigenvalues, let's look at the equation lambda I minus a times x equals 0. So I'll rewrite my matrix, but not the determinant. So that's lambda 0, 2, minus 1, lambda minus 2, minus 1, minus 1, 0, lambda minus 3. And I'm multiplying that by an arbitrary vector, x1, x2, and x3, and I'm going to see what restrictions are on x1, x2, and x3 in order for this to be 0. Okay, so let's do it for lambda equals 2 first. Why not? If lambda is equal to 2, then that implies that this thing with 2 plugged in for lambda becomes 2, 0, 2, minus 1, 0, minus 1, minus 1, 0, minus 1. And I will multiply that by x1, x2, x3. Okay, so that should be 0, 0, 0. I'll adjoin the matrix again. So I get 2, 0, 2, 0 by augmenting it. Minus 1, 0, minus 1, 0, minus 1, 0, minus 1, 0. And reducing this, notice I can cancel out both of these rows using the top row. So I'll just have 1, 0, 1, 0 after dividing by 2, and zeros everywhere else. Okay, so that means that I just have a top equation of x1 plus 0x2 plus x3 is equal to 0, which is the same thing as saying that I'll make x2 and x3 my free variables, so I'll make x2 equal t, x3 is s, which means if I subtract 3, I get x1 is minus x3, so x1 is minus s. x2, I said, would be t, And then x3 I said I'll make s. Okay, so now I have x equal to minus s for x1, t for x2, s for x3. And I'll separate the s and the t this time. So I'll write minus s 0 s plus 0 t 0. All I did was split up this vector into two vectors that add up to it, so that I'd have all the s's in one vector and all the t's in another. Okay, now I can factor out the s in the first vector. I get s times minus 1, 0, 1 plus t times 0, 1, 0. Great, so that means that I've got two vectors in my basis. I've got minus 1, 0, 1, and I've got 0, 1, 0. Those guys form a basis for the eigenspace corresponding to lambda equals 2. Okay, we still have one more lambda, right? We have lambda equals 1. Let's examine that. Okay, so for lambda equals 1, we'll do the same thing, but plugging in 1 gives me 1, 0, 2 on top, 1, 0, 2, then minus 1, 1 minus 2 is minus 1, minus 1, minus 1, 0, and minus 2. Okay. And then I'll multiply that by x1, x2, x3, set it equal to 0, 0, 0. I get 1, 0, 2, 0, minus 1, minus 1, minus 1, 0, minus 1, 0, minus 2, 0 for my augmented matrix, and then I will reduce that. Notice the last row is a multiple of the first, so I'll zero it out. And then the first already has a leading 1. I'll add it to the second row to cancel out this one and get a leading 1 there. And then just multiply by negative 1. So I have 1, 0, 2, 0 still on top. My second row without this guy, after adding this, becomes 0, minus 1, but then I'll multiply by minus 1 to get 1. And this is still minus 1 because I added that. And then my last row is 0. So I get a top equation of x1 plus 0x2 plus 2x3 equals 0. And I get a second equation of x2, because there's no x1s, minus x3 equals 0. So that means that I have x3 as a free variable, but not x2 this time. So I'll set x3 equal s, and I'll write x1 and x2 in terms of it. So if x3 is s, that means that x2 is also s, because I just moved this to the other side by adding it. So that means that x1 is negative 2s by moving this to the other side. So I get x1 is equal to negative 2s, x2 is s, and x3 is s. So I can write out that x equals negative 2s, s, s, which is s times negative 2, 1, 1. So that means that negative 2, 1, 1 is in and of itself a basis for the eigenspace corresponding to lambda equals 1. Okay, next up we have that a square matrix A is invertible if and only if lambda equals 0 is not an eigenvalue of A. How about we prove this? First, let's assume that A is an n-by-n matrix, and we'll observe that lambda equals 0 is a solution of the characteristic equation if and only if the constant term Cn is 0. Right? Because if I plug in lambda 0 for all these guys, then I get that the last thing there has to be 0. So that means that to prove that it suffices to prove that A is invertible if and only if the constant is not 0. If the constant is not 0, then that means that lambda equals 0 is not a solution to the characteristic equation, which means it is not an eigenvalue of A, and it means that we're done if we can show that A is invertible in that case. Okay, so then take a look at the determinant of lambda I minus A. Remember, that's the characteristic polynomial, so we'll set lambda equals 0, and we just get determinant of minus A. But that means that lambda is 0, that would just be Cn. Okay, so that means that's the same thing as taking that minus outside by taking minus 1 to the n. That's what happens when we remove constants from determinants. So it follows from the last equation that the determinant of A would be 0 if and only if that constant term is 0. So if the constant term is not 0, then that means the determinant is not 0 and it's invertible. If the constant is not 0, then that means that lambda equals 0 is not a solution, so it's not an eigenvalue. So there we go, we're done. Let's verify this theorem for the matrix that we looked at in example 7. So we'll look at the determinant of A, which is equal to 0, 0, minus 2, 1, 2, 1, 1, 0, 3. And notice that's negative 2, negative 2 times negative 2, which is equal to 4, which is not 0. Remember, that's consistent with what we saw in example 7, since we got eigenvalues of 1 and 2. There was no lambda equals 0, which makes sense. We got determinant on 0. Great. So we can now add a couple more statements to our equivalent statements, or really just one more. We now have that lambda equals 0 is not an eigenvalue of A, is the same thing as A being invertible, and that means that it's the same as all the other ones that we already saw were equivalent to A being invertible.